Hey, welcome back. I've shown gear cutting with module gear cutters in the past at several occasions, and that will not be the main topic of this video. More grinding a tool to do said cutting without having to rely on commercial available cutters. But Stefan, you can buy module gear cutters. Yes, my dear friends, that is true. But there are like three options. Those very janky USSR gear cutters that I used in the past. They're really not great for the most part. The gear profiles on mine were anything but symmetrical, and the back relief was turned very rough. And it's hard to get a good cutting edge if the clearance surfaces have such a bad surface finish. I don't say that's always the case with the USSR gear cutters, but mine were really not good. Then you have the options to buy solid carbide module cutting heads from a company like P. Horn. Those are great, I suspect. I have not tried them, but that's the one company that I always bought other tools from, and those tools always did exactly what they were supposed to. But those are really expensive. And option 3 are high-end, high-speed steel module gear cutters, but those get exceedingly rare to be found. I don't know if anybody in the Western world even makes them anymore, apart from very small specialized gear cutters for watchmakers. Module gear cutters are always a compromise, since you have to create all the gear tooth shapes from 10 teeth up to indefinitely many teeth, like a gear rack, with only 8 and in some cases 16 cutters. So each cutter is always a compromise, and it's made that the profile of the gear cutter matches the profile of the lowest number it's supposed to cut. So as you approach the upper limit of teeth that you can cut with one of those cutters, the error in the profile gets bigger and bigger. So I figured I would precision grind myself fly cutting inserts matching the gear profile for the tooth count and module combination that I need to reduce the overall error. There will be a little bit of an error in my method, but I will mention it later. But it's still like an order of magnitude better than the USSR gear cutters that I had. So let's get grinding. I have the punch grinder here set up as a radius dresser. Normally when you buy one of these, you have the option to get an additional dressing arm for radii along with it. And that's a goosenecked holder. And the gooseneck shape is primarily there for one to clear the wheel and also to give you more larger adjustment range without running out of travel with the V-block here. As you can see with my setup here, the V-block is already sticking out of its guiding slot by about 8 millimeters. And I'm only doing a 1.5 millimeter radius dress. So this is not ideal. I took this is a boring bar for a boring head, I think, and I put in a single point diamond, and I adjusted it kind of vertical at the 90-degree position. But how do you set the radius of this thing to at least approximately to what you need? I find that using gauge blocks is kind of the easiest way. You need to know the center height of your punch grinder. It's about 80 millimeters on this size usually. The exact number is usually on a plaque on top of the punch grinder, punched in. Somebody removed this plaque from this punch grinder before it came to me, so thank you very much for that. But I measured it, it's pretty much 80 millimeters, and this setting method is not highly accurate anyway, so I have to do some tweaking. But the idea is you put your punch grinder on a surface plate, or in this case on the table of a drill press because it's just demo. You build a gauge block stack that's the height, the center height of the indexer minus the radius that you want to dress on your wheel. minus for a convex radius and plus for a concave radius. But we want to do a convex radius. 80, the center height minus 1.5 gives us a 78.5 millimeters. And that's this gauge block stack here. And when we put this next to the diamond, you can see, yeah, and it's in its lowest position, kind of level. But how do you really check it? Well, you take an additional gauge block, make sure that since we're here in the grinding area, everything is cleanish, and you slide it on the stack, but you let it overhang. And in an ideal case, use an old gauge block up here, because there's a chance of scratching it when we move over the diamond. We're looking sideways at the diamond here, and we're looking sideways at the gauge block stack with the single overhanging gauge block. So now we just give us the option to swivel back and forth, but basically we want to be at the lowest point, so I'm indexing it at the lowest position. Then you bring your gauge block in, and then it's a matter of moving the diamond up and down, either by losing the set screw and sliding the actual diamond around, or you use the built-in adjustment for the V-block here. And the idea is to make the diamond contact the gauge block ever so slightly early, just by looking at it and eyeballing the light gap between the diamond. It is a little bit hard because the diamond doesn't have a it's a kind of irregular shape up here, and you have to do your best guess what's the highest point. So that's the way to set the radius. These punch fixtures have two ways of indexing. Well, three. For one, they have a graduated dial and a vernier back here, and you can lock them with the screw here in every position that you want. Then they have a 15-degree direct index. This is this pin up here that you can just index, and you can also fully disengage it if you want to do larger sweeps. And you have these adjustable stops, two of them, one here and one down here, that can act against this pin that you can engage, pushing it in from the back side. This can be set to any angle combination that you want. And this is what you're going to use to dress the radius, because for a full radius dressing, well, a half of a radius, we need a full 180-degree sweep of the diamond. And the way we set this is we could use, for example, the dial on the back, but it's easier just to use the direct indexing. So we index it so it's horizontal. We engage the stop pin here, and then we loosen the screw of this block and we move it up against the stop pin. I don't do this right now because there is grinding dust and I don't want to clean it, just for a little bit of demo. Then we sweep it 180 degrees, index, and we move this stop block also up against the stop pin. And this allows us now to do a nice 180-degree sweep with our dressing diamond without having to think about overshooting or trying to hit the index while we're looking at the diamond, the grinding wheel. And that's a lot of stuff to look at the same time. So it's nice if the stops are just there and work. One less thing to mess up. Okay, let's set it up on the surface grinder. Okay, over at the surface grinder, and we start just giving the magnet a wipe with a tissue paper and some alcohol. I think there had been some rust preventive from the last time I used the grinder. This is, by the way, just a rehearsal. I did all of this already, and in hindsight, I thought, it would be neat to film it, because that's a technique rarely shown. both the radius dressing with the punch grinder and doing the step over grinding. Both of them are kind of rare here on YouTube. So I basically did a practice run, and you get the condensed down version where I already have figured out everything off camera. So way less cussing and head scratching. And in reality, the figuring out part doesn't make for good video. So for dressing, you want the diamond to be on the lowest position of the wheel. That's quite easy. Just drop the wheel down. This will take a moment. This is a 1mm pitch per revolution elevation screw. So, is it? Yeah, it's 1mm per rev. So this will take a moment. We're back after a short break of cranking. I'm using a fairly small wheel here because this is only 4mm wide. And I didn't want to dress off a ton of material. That usually ends with sandstorm. And this wheel is 100 grit, and it's a hardness, let me check. So that's the wheel. That's a 100 grit hardness K. So fairly hard binding. You can't do a lot of material removal with this wheel or it will burn up your work. But for profile grinding, that's a good wheel. Still in the process of finding the low spot of our wheel, and I'm just dropping down ever so slightly with the wheel until I hit the diamond. And you have to be super careful because you can crack the diamond doing this. If you want to protect the diamond a little bit, use a piece of printer paper in between. This gives you about 0.1mm of cushion before you crack the diamond. You want to find this point where the grinding wheel is dragged along by the paper and the diamond behind it. Then you want to find kind of the center of this short rotational movement, like here. And that's the position that you put your table locks in. So there we go. That's our position in relation to a spindle. You could also put a square here on the table and just eyeball through the diamond and through the spindle center. That's also good enough. But I kind of like this method. It's fine for this purpose. It's not a high precision radius that I'm doing here. Well, it kind of is, but it's fine. So I will remove the radius from this wheel, and then I will redress it as a radius wheel on camera. Okay, I removed the radius from the wheel, and it's hard to tell for you, but here you can see that it's definitely not a radius wheel. So let's dress the radius. The wheel is already dressed to 3mm width. I won't remove all that material. That would just be a horrendous waste of material. So I need to touch off with the diamond. For that we swing the diamond to the horizontal orientation, like this, and move it over. And note that I wrapped some aluminum foil or tin foil around the entire head of the indexer. It's not in the way, but it keeps a lot of the flying grit out of the workings of the dovetail adjuster. It's not in the way, and it reduces the amount of cleanup I have to do afterwards. That's a good thing, I would say. We swing this to 90 degrees. We drop the wheel down until it's past the wheel, and now you can not see anything. Let's do it on the other side. I think you can see it better over here. Let's do this. and swing the diamond over horizontally in the under orientation. Move the wheel over, drop it down. And now with the wheel spinning, I will just touch the diamond ever so slightly. You will immediately hear it. And that's when we have to stop and zero out the DRO. You could do this by spinning the wheel by hand and approaching the diamond. This is fairly sensitive and you will get a very good feeling. We can do both methods. So moving the wheel by hand and then approaching the diamond very, very slowly. This can take a moment. How's your day going? Mine was great. I was out for a hike. Got rained on a little bit. There we go. Did you hear that? That's the wheel touching the diamond. I'm zeroing out the cross traverse of the surface grinder now. And I'm backing off like 5 microns, still touching, moving off, another 5 microns, and not touching anymore. Okay, that's my contact point. That was 7 microns off from my initial touching, so not too bad. Moving away, moving C a little bit because maybe I have worn a little groove into the wheel now. Now we'll do the same with the spindle running. I think you can hear it through my microphone. Let's see. There is the contact. It's a little bit hard to tell through the microphone. I will try to boost the loudness up a little bit, but I think it was easier to hear in the first method that I showed you. Okay, and that's all we need. Normally, I would now dress the wheel to 3 millimeters width. And now it's just a matter of swinging back and forth here and slowly dropping the wheel down and seeing how the diamond eats away the wheel. It's kind of cool to watch. So this is the best I can do without putting the camera behind the grinding wheel. I don't want to have the camera in the shooting line of all the sand. I don't like the lens or the UV filter that I have on the lens to be sandblasted. So I hope this is good enough to see what's going on. And I'm just taking 180-degree swings while after each pass dropping down the C-axis by like 50 micron. And now you can hear that the diamond is taking a full cut across the 180 degrees of our swing motion. There we go. Let's take a final cleanup pass, 20 microns, with a very steady feet, and then move the wheel out of the way. There we go. That's dressing a defined radius on a wheel. Let's pull the radius dresser or the punch grinder off the machine and have a better look at the wheel. Here we can see the radius that would rest on this grinding wheel. Doesn't look too bad. This grinding wheel has some discoloration in it, so that's the reason for this weird spot. That's not my blood. I recently touched a grinding wheel, by the way, and some people mentioned that I had an infection on my knuckle. And yeah, I had very much an infection because grinding wheels are dirty and they smear a lot of dirt in a wound. So if you cut yourself on a grinding wheel, see a real doctor, please. Okay, that radius is all nice and dandy, but it would be nice to verify it. But you could use, for example, a radius gauge, or you can measure it optical. I'm in the fortunate position to have a measuring microscope that I can use, but I can also check it with gauge pins. But for that, we need a negative of what we dressed on this wheel. And traditionally, very classic for doing a grinding wheel shape test coupon would be either a piece of carbon, like you would use for EDM electrodes. If you have that around, that's a good material because it doesn't wear the wheel, or a razor blade, what I showed you earlier, and we'll just plunge the wheel into it. That gives us the exact shape that the wheel creates. So let's set this up for plunging the radius, and then we'll measure it both with the microscope, and we will also inspect it with gauge pins. So I buy single edge razor blades in the bulk because they are kind of useful for a lot of things, including doing coupons for grinding wheel contours. This is a little bit annoying to do. Let's see if we can make our life a little bit easier with some parallels. I can't directly clamp on the razor blade because it has this strong back. So let's drop this in between here. Make sure we're clamping on the wheel on the razor blade itself. Make sure it's halfway seated. Clamp it down, and now we just grind our radius in there. First method is to check it with gauge pins. If you don't have gauge pins, I'm in the fortunate position of having gauge pins in a 10 micron increment, which is very pleasant to work with. If you don't have that, you can use drill shanks. You can use transfer punches. Those are nicely stepped, of course, in a way coarser increment, but it's better than nothing. And you also can turn just pins to check what you're doing. Okay, we start with a large pin. This is 3 millimeters. And I already know that the slot is undersized because I already did this before and I didn't change the setting of the punch grinder. So dropping the pin in here. Ooh, you can already see that we're not dropping in there. So let's go down to 2.97, 30 micron under. Already drops in further. 2.96. And that looks good. But there is still a tiny, tiny light gap on the underside of the pin. It's hard to see from the camera, and I cannot get a better shot, to be honest. Maybe this is really hard to film, but you're smart, you get the idea what's going on. But here you can see the light gap between the pin and the ground slot in the razor blade. You can see the light shining through here on the right side of the pin. Let's take a 2.95, drop it in here. That's looking good. The alignment with the slot also makes a difference, of course, but this looks very, very good. Oops. There's a tiny light gap on the side, so I would assume that the slot is 2.95 plus a tiny bit. Plus because the light gap is on the side of the pin and not on its root down there. But so with the pins you can get a very good understanding what you made here. But now let's go to the microscope and check it for real. We're over at the Nikon measuring microscope. And yes, I still have not finished the X-axis lead screw. Well, the lead screw is finished, but I still have not made the replacement half nut. And yes, it's annoying, and yes, I simply don't have time to do it. So at the moment I'm pushing the X-axis around by hand. The precision is still there because the linear scale is independent from the lead screw. But yeah, it's annoying, and I hope to find some time to do it. And yes, I will do part 2 of the video at some point in time. So let's measure this radius here. I just have it on top of a pot magnet, so it sits up here and is easy to measure. So the idea is to line up the crosshair with 3 or more points on this radius, and a quadro check, the DRO of the microscope, will automatically spit out the radius, the diameter, and the position of this curvature. And yeah, I did the measurement now 4 times for filming purposes. I measured it beforehand 1 time, then I had to measure it filming the wide shot, then I had to measure it filming through the microscope, and now a last time I had to film it again to show you the quadro check readout. And it's always 2.96 and some change. Optical measurement has some issues with repeatability. It's very depending on your ability to line up a line with an edge. In this case it's fairly easy because we have a high contrast situation because I'm using the green light from behind the part, but still there is some uncertainty, and that's usually the micron decimal point that's moving around a little bit. But a toolmaker's microscope is a very good solution to measure features like that. So yeah, 2.966. In an ideal world, we would create our toolpath or our increments for the DRO with exactly 2.96, or we just imagine that it's 3 millimeters, respective a 1.5 millimeter radius. That's fine. How does this grinding wheel help us now? Well, we can use it like a ball end mill on a CNC milling machine and just trace out a contour with it, like this. Imagine the washer being the radius of the wheel. And we're looking straight onto the contour. So we grind here, we move over, we grind a little bit, we move over, and we follow the contour like this. It's exactly the same technique as I have shown in the manual CNC video maybe a year ago. It's almost like etch-a-sketch milling or grinding. And back then I already mentioned that with this technique you can also do profile grinding. And if you watch An Engineer's Finding, Alex, the exact same technique on the D-bit grinder to grind a fly cutter to mill a new worm gear for his Walter indexing head. We need basically coordinates. Our 0 position is center line to our tool blank, like this. So centered in this orientation. And the underside of the wheel touches the top of the tool blank. That's our 0, 0 position. Here.
0, 0. Then we have increments. We move minus 0.189. That's here. That's the tangent point before the radius here drops off. It's still C0, doesn't move. We move over minus 0.5 and we drop down 22 microns. Drop down. We go to minus 0.6 and we drop down to minus 41 micron. Minus 0.7 in X, minus 0.053 micron. Drop down. And so on and so on. And always at some point it will start to change rapidly. That's always when you're past the 45-degree contact point. Then it starts to change very rapidly, like here. X minus 1.9 is C minus 1.062 minus 2. And then it drops down by 0.3 millimeters. Move over another 0.1 millimeter and it drops down another 0.5 millimeters. I think that's that's about here. This part of the contour is very steep. So any small change in X will result in a very large movement in C. So with all these numbers, we're ready to go to a grinder and just grind this profile. It's very easy. So let's do that. Let's grind a piece of high-speed steel into the shape that we need. Let's grind the fly cutter cutting insert. And I found a nice piece of high-quality high-speed steel. And we don't have any special requirements for work holding. You could use, for example, a vertical standing indexing head, but we don't do any indexing here, so a vise with a V in the jaw is good enough. Just needs to be vertical. You can also use just a V block or whatever you want to make a block with a clamp. Doesn't really matter, just needs to be stable. 6mm diameter. I want the grinding wheel to be centered on the cutting insert, and that just makes our life later way easier. For touching off the sides, we just go to one side and we touch off with the wheel. There we are. There was a little noise. We zero out the DRO. We move over and we touch with the wheel on the other side. We can do this because the wheel and the radius are centered to each other, because I dressed the sides of the wheel. That way everything that we will do when grinding this cutting insert will be on center. There we go. Our display shows 8.969, that's 8.97. 8.97, 8.97 divided by 2 is this, 4.485. 4.485. And when I crank to 0 now, the wheel is nicely centered up on our blank. Now we just need to touch off on the top of this bit and we're good to go. Note that I not have cut the top rake surface yet. I will do that after I have profile grind everything. You can split it before. I could, when I did my first insert, I split it on the D-bit grinder and then I came over here and did the rest on the surface grinder. But let's do it this way. I think you can see quite well what's going on in this orientation. I will just grind the top of this blank flat with this radius wheel with a small step over. This will give me a very precise 0 for my height. Okay, let's turn on the Okay, and now it's just moving the wheel by the numbers that I have written down and stepping my way around this thing. Let's start on the left side. Okay, that was the first step. Only 22 microns deep. So let's move over next increment and we drop down another 20 micron. Next increment. Okay, that's the first side of the cutting insert. Let's move the wheel clear. Move back up. Now we will do the second side. But you can see this doesn't take too long. This first side took me about 10 minutes. On to the second side. Using the same coordinates, just with a different, just going into positive direction X. So we start here and we'll just walk the same profile over here. And then we will have a nice symmetric gear profile. If you wondered about the filming setup, Canon 77D, I replaced my old 700D that had been dying with a used 77D, which is a nice little upgrade. It's not a high-end camera, but it's way more camera than I can use or need. The famous 18-55 kit lens, and it's filming in here right in line with the wheel. Tripod with the folded over top arm, weighed down with a sandbag. And somebody asked about when I last showed this tripod. This is a K&F concept tripod. They have a web shop. They are very reasonable priced compared to something like Manfrotto, and they have a lot of options, especially if you want a horizontal or adjustable top arm. So I have been quite happy. They also have a ton of options for the arm on the end of the tripod boom. I went with a very simple ball mount, but they also have like 3-axis heads or even fluid heads. I don't need that since I don't do tracking shots. Ball mount is quite nice. But I mounted an old Manfrotto quick change base that I had laying around on top of it, since I have a lot of these plates here. So back to grinding. Looks like a gear profile. Now we want to split it in half to get our top rake for cutting. And we can do that just by moving the vise on a mag chuck and then plunging down with a grinding wheel, with a straight grinding wheel. Get this off. Oh, oops. Clean the magnet. Always clean the magnet. Otherwise it scratches up like mine. Doesn't hurt to give it a wipe with some alcohol from time to time. And we put on the vise with the cutting blank. Since it's square, the vise, it will register nicely against the side rail. 80 grit wheel. This is a seated gel wheel from Norton. 3SG5, I think. A 3SG, 60 grit, excuse me. Just touching off. There we go. It's not a high precision touch off. We're just splitting it in half at 3 millimeters. Plunging down. There we go. There's the finished fly cutter. Nothing else needed to do. You might notice that it's a straight ground profile. There is no back taper for relief, and that's on purpose. That's doing that on a profile is quite a pain. That's really the territory for dedicated tool and cutter grinders. On a surface grinder, that's a headache. So what I figured is I put this above center line in a fly cutter, and this solves the problem of not having clearance. In theory, that's the same technique as if you use a threading insert on a lathe. Those have also no clearance, but they are tilted forward, which is the same effect as putting them above center line, and that creates the necessary clearances.
Let's see how we create the shape for the tool that we want to grind, or any other profile in reality. So we need a body. I'm using FreeCAD here because it has a very competent gear generator plugin, and Fusion annoyed the everlasting crap out of me. So currently on FreeCAD, we need an envelope gear. Let's do 10 teeth at a module of 1.75, pressure angle of 20 degrees. And down here we have an option for profile shift. You need this if you have a set distance of between two shafts, but you have also a set gear ratio, but you still need to adjust a little bit, and then you can use a profile shift. This will change the shape of the teeth in a very funny way at some point because it breaks. But this allows you to bodge it a little bit. Well, it's not a botch, it's a standard practice in gear and gearbox design. We're not doing this here today, we're doing a standard non-profile shift gear profile. Okay, that's our 10-tooth gear. And I like to extrude it then, just to have it as a solid, just something, so if we look at it sideways, we have something to look at. Now that we have our gear, we want this gap in between here as our tool shape. For that we create a new body for the tool, so it's a little bit organized. We can even name this out here. Let's do rename. This is gear, and this is fly cutter insert. make this a little bit wider. And let's see. Okay. We do a sketch up here, and unfortunately we cannot project these curves of the involute curves of a gear. This doesn't work for some reason. However, this is handled internally in FreeCAD. It doesn't allow you to project this kind of curve onto a new sketch. But what we can do is we can project the endpoints. And these segments are very, very close to a radius. And we can just do a 3-point radius curve, and we can approximate it like this. And yes, there's a little bit of error, but that's in the micron range, especially when you zoom in and do a nice job of aligning it. You could also play around with tangent constraints to make it a little bit more solid, but for the sake of this demonstration, this is fine, I hope. Let's close this contour. Yeah, there is a polyline tool too, but let's close this and make this line down here horizontal, so it closes the contour. And this extension here needs to be, well, this should be tangent to this. Would you please? And we give this a 3mm radius because we could use a 6mm blank for this. Okay, and that's our closed contour. Hit finish sketch. There it is. Now we can do a extrude minus, it doesn't really matter, -3. Let's do OK. The gear is still here, it's just hidden. And we mirror it over, let's see, base. Yep, that's that's our fly cutter. And I just realized that I want this to be 6mm, not 3mm. Go back like this. And it's a round tool bit, so we go on the back side, we add a sketch, we project, we add some reference geometry here. This is absolutely not a FreeCAD tutorial. I just want to give you an idea what how this can be done. And we cut away everything that's not round. Let's do through all. There we go. That's the tool bit. If it was a full 6mm round blank. And now we cut away half of it. Yeah, I should dimension these sketches, but I won't. I could also constrain this properly, but I won't because this is just a demo. And we're just carving away a bunch of material here. Oh yeah, there is a little bit of material left, so let's do two-sided and do the other side through all, and this should take care of it. Okay, there we go. And if we put the gear back in, let's make this a different color. Well, oh, excellent. This has a button random color. That's neat. So there is our fly cutter profile that we want to grind. It doesn't have clearance, but we can hide the gear. And now we go into a sketch that's on this axis here. Oh, thank you for flipping it around. and we project this line here. Well, can we? This line here, and we add basically the fly cutter diameter. Let's say we want to set the fly cutter to be on a 40 millimeter diameter, and if hello, would you please? Hello? So, if this top surface here of the fly cutter is exactly on center line, which would be a 0-degree top rake, we don't have clearance down here. The backside of the tool will not only rub, it will very heavily collide with the material behind the cutting edge. That's not good. That's a, as we call it in the industry, that's a problem. But we can, there's a little trick. This part of the video is me saying quite a lot. So make this vertical. And now when we dimension this like in 1 millimeter, yeah, now we can put the tool above center line. Let's go back to this. Let's go back to this view. And as you can see, if I put it 2 millimeters above center line, it already clears down here, mostly. Let's put it 3 millimeters over center line, and then it's fine. This looks very precise. So, put it above center line, it will cut fine. It's basically a negative cutting geometry at that point. It's basically a negative 8-degree top rake, but a sharp tool will cut with a negative top rake. Not a problem. It will perform a little bit less nicely, but it will still leave a very good finish. And well, that's the trick to make a zero clearance tool or a zero back clearance tool cut very nicely. I will show you in a moment the footage of milling a gear with this cutter. But I just wanted to give you a basic understanding of how to design the tool in CAD. And now that we have this, we still need our contour to grind. Let's hide the sketch very quickly. And for designing the contour, we go back into a sketch and we project these curves that we now can project because they are drawn geometry. And we add a circle, which is our tool. Let's say this is, as I said before, dealing with a 1.5 millimeter radius grinding disc. Let's do this at 3 millimeters. So 1.5 millimeter radius wheel, and it helps if we have a line that we can measure to. So, and we want this dimension, which is basically our plunge depth. Make this a reference so it's driven. So when we when we move the tool, when we move this shape around, this number here follows accordingly. And we can do the same with a dimension of the center line, like this. And now we have the choice of either entering numbers here to move it around, or we make this a reference dimension 2, and then when we pull the geometry around, both X and C will follow accordingly. We could now eyeball it into position into the shape and just read the numbers. That's a little bit coarse and a little bit cursed, but we can do nicer and a little bit more process reliable. We can do, for example, a tangency between those two. And now if I just move this along, this circle or tool is stuck to the contour. And for every position where I move the circle, it will give me always my X and my Y, or my C coordinate, my plunge depth. You have to think upside down here. Like this. This is how it's oriented in the grinder. But now the number here is upside down because FreeCAD doesn't respect the monitor orientation. But it's fine. You get the idea. Each time when I say you're smart enough to understand this, I'm offloading my responsibility to do a good explanation and just tell you to put your own work into it. I'm just kidding. So you have to do the line segments separately because you cannot do a full a tangency constraint along the full length of this contour. You have to do it in segments. So now the tool is, in quotes, stuck to this to the straight part here. When we remove this tangency, we can also stick it to the radius up here and get all our coordinates that we need by just moving around like this. Okay, that's basically how you create those toolpaths. There is 100% a better way. There is probably a way how to automate this in FreeCAD using scripts. There is also a way of defining the gear tooth curve just by formulas. So you could do this in a spreadsheet. One could do it in Python, loading a DXF contour, and it would spit out all the coordinates automatically. I'm sure there are a million better ways than this, but heck, it works and it's fairly simple. You could even do it on paper, draw out the shape of the tooth with a V profile template that you roll around to create the correct gear profile. And extract your toolpath like that. So there's a million ways to do it. This is one way, and you have to play around if you want to do it like this or with this technique.
This is the fly cutter with the cutter above the center line being made. It's a very simple design that works well enough. You have seen it in use in the beginning of the video. I can't really show the full part, but it was held between centers on the index on a long arbor, and the cutting was done with the horizontal spindle. This has the nice benefit of allowing to do a climb cut. Because of the very heavy C and X axis combination of this mill, there is no danger of the work self-feeding when climb cutting in this orientation. And here is a microscope shot of the gear profile after doing a test cut in a piece of aluminium. By comparing X and Y coordinates of the profile between the microscope DRO and the CAD, you can verify if your cut profile is close or not. I have to give a disclaimer. Putting the cutter above center line will create a profile distortion, and you have to take that into account for precision work. You can or have to do the correction compensation while designing the cutter in CAD by respecting the center height change by putting it above center line and the resulting top rake. Similar to how a lathe threading insert is not ground to a 60-degree included angle because of its tilted nature. But if you need to do that, that's an additional step that you have to figure out. You can also compare how much error it creates compared to a uncompensated profile, and if that's a problem for your application.
This cutter is like, even without compensation, this cutter would be like an order of magnitude nicer than the old module gear cutters that I had. Okay, that's all I have to show this time. Usually in the end I always tell you that I try to get the interval between the videos shorter, but in reality I'm very busy with customer work where I can show less and less of the actual work due to its nature in R&D and the underlying NDAs. But as usual, I still try to film as much as possible about the process and the tool making that goes along with it. I hope you learned something. Thank you all for watching and your ongoing very kind support. I'll be back.